We have just a little bit left to do with our polynomial functions before we move on to chapter 6, and that's going to be some applications of polynomials. So first of all, I apologize in advance with the construction going on. It's really loud. Hopefully you'll still be able to hear everything okay. Here's our first example, and I'm only going to do this one example. Some of the equations you see that we'll practice with are ones that I really just kind of want you guys to think about, and you have the knowledge base to be able to solve them. So here's our example. The estimated number V in thousands of electric cars in use in the United States is, and here's our function, where T represents the year and T equals 1 represents the year 2001. So if T was 2, that would represent the year 2002 and so on. We're going to do a couple things with this. The first part is to use a graphing calculator. To graph the interval T is between 1 and 10. And we want to describe the graph on this interval. So we go to our graphing calculator, and we need to type in our equation, which is pretty long. We have 0.151280 t cubed minus 3.28234 t squared plus 23.7565 t minus 2.041. And instead we want to graph on the interval t is between 1 and 10. That's really helpful because if you look at your equation, that's what our t is, what our x value is. And that's going to help us figure out what window we really want to look at. So we set our x values between 1 and 10. And if I go graph, as you can see, this really doesn't give me an idea of what our function looks like. But if we know our x values, remember that zoom fit option we can use. So go to zoom, down to fit. Again, our calculator will find what the lowest y value is and what the highest y value is based on our x values. And this gives me a really good picture. So if I look at my graph here, keep in mind the context of the problem. T, our x values, that's our number of years. And then our y values, our V, that tells us how many thousands of electric cars are in use. Okay? So if I look at my graph, my y values grow really, really quickly at first. The number of electric cars are increasing pretty quickly. So our y values grow really fast at first, but then they level off for a little while, and then they keep going up again. So when I'm describing the graph on this interval, that is the kind of thing that I'm going to take note of. The function increases quickly at first, then levels off before it increases again. And hopefully that kind of makes sense if you think about our situation here. Right around 2000, a little bit after 2000, that's when electric cars or our more fuel efficient cars were really coming into play. So the number of cars in the market increased really quickly at first. Then it kind of leveled off. The people that had them, or the people that wanted them, already had them, and then they started to increase again, with some more people either needing to replace their car or just more people realizing that fuel efficient is good. That's part A. Part B, find the average rate of change. On the interval. Between, in this case, 2001 and 2010. Now, rate of change you've heard before. Sometimes we kind of think that, or we kind of forget what rate of change means, but rate of change is really looking at the slope. On average, in this case, the average rate of change is really going to be the slope between our first point at when x is 2001 and our last point when x is 2010. That'll give us the average of how our function is actually changing. Now, since our function is a curve, since it's cubic, without using calculus, we don't really know what the average rate or what the exact rate of change is, whereas a line, that rate of change is constant. It's not here. But we can figure out, like I said, what our average rate of change is by figuring out what our y value is when x is, or when our time is 2001. So I want to write two ordered pairs here, 2001, 2010. And I need to figure out what my y value is. Now, I could potentially do this by taking 2001 and plugging it in to each t in my equation. I'm going to show you a way to do this on the calculator too, just because it's a helpful thing to know. So if I know the x value, I can go to second calc here and then click on value. I can enter in an x value, it'll tell me what the y value is. Oops. But in that case, as you just saw when I tried putting in 2001 isn't actually on my graph. On my interval though, remember we said the year 1 represents the year 2001. So what I really needed to do was have a 1 here. I'll have to round here too, but 18.58. And if I want to find my y value when x is 2010, my calculator still kind of knows that I'm in that second calc value mode. So I can just type in, again, I don't want to type in 2010, I'd want to type in 10. Okay. Type 10, hit enter, and it's 58.57. Now we can find that average rate of change. Your slope, remember, slope is y2 minus y1 over x2 minus x1. In this case, I'm just going to use 58.57 as my y value, or as my y2. And I guess I really shouldn't have had this as 2001. I should have had this as 2000, or as just 1. And I should have had this as just 10. Okay. It really means 2001 though. So 58.57 minus 18.58. It's 39.99. Over, again, this should have been 10, this should have been 1, but either way we get 9. It's 4.44. All right, so my average rate of change is 4.44. Now think about what this means. Remember that y value is the number in thousands of electric cars. and our x value is our year. Remember 4.44 is like saying 4.44 over 1. If I kept my labels here, then it's a little bit easier to think about the real world meaning behind my rate of change here. Since it's positive, the number of electric cars is increasing by 4.44 thousand each year. Okay, and again, that's on average. On average, 4.44 thousand each year. And then part C, just one other thing to think about here. Do you think this function could be used for years either before 2001 or after 2010? Oh, let's look at our graph again for a second. My graph looks like this. Let's look at our equation again for a second too. My equation is cubic, so remember what the ends are doing. My end on the right is going to keep going up forever. The end on the left is going to keep going down forever. So in this problem, where our y values is the number of electric cars, that's not going to make sense because that means eventually I would have a negative number of electric cars. Probably not going to happen. And same thing with the right side here. As our time increases, we aren't going to have 8 trillion electric cars in the United States. That's just not going to happen. Even if everybody in the United States had an electric car, we're not going to reach that big of a number. Okay. So I'm going to say no. Since the degree is odd, that would mean there are negative cars. And also that the number of cars keeps increasing. Forever, and that's not going to make sense. Great. Now next class we'll have some application problems. You might see a problem like this, but other just kind of applications in general that hopefully will get you thinking not just about the math, but actually the real world applications behind it.